Good morning and welcome to a dissection and analysis of the 2004 Sterigenics explosion. On August 19, 2004, ethylene oxide exploded at the Sterigenics facility in Ontario, California. The event occurred when ethylene oxide was released to an oxidizer. The chemical readily ignited, thereby breaking the glass of the control room and injuring the 4 people inside of it. When the tank exploded, the chemical released out into the open, causing 6,000 people in nearby towns to evacuate their homes. Fortunately, there were no fatalities. The massive explosion was caused by a series of systematic failures, and this video aims to identify all safety breaches and how to prevent or mitigate them in the future. Sterigenics International used ethylene oxide in order to purify medical equipment. Items such as bandages and needles are placed inside of a chamber, which is then closed and permeated with ethylene oxide. The sterilization step lasts a couple of hours as all bacteria and microorganisms need to be killed. Finally, the ethylene oxide is carefully removed from the chamber in a series of steps as it is a very poisonous and flammable gas. During the proper removal cycle, first about 60% of the ethylene oxide is purged to an acid scrubber. Then, the remaining 40% undergoes a series of gas washes using nitrogen and oxygen. Finally, there is still a small trace amount of potentially toxic but not usually flammable amount of ethylene oxide in the chamber. This is backvented to an oxidizer. On the day of the incident, these procedures were not implemented properly. In the early morning of August 19th, mere hours before the explosion, the control system indicated an EO system failure in the sterilization chamber. The operators correctly aborted the cycle, moved chamber contents to an aeration room, and called in maintenance to inspect the EO system. In the process of testing the EO addition system, maintenance closed the chamber, added EO for calibration tests, and performed the initial evacuation to the acid scrubber. Since no medical equipment was inside of the chamber, the eager maintenance technicians asked for permission to use a gas wash bypass, as they believed that gas washes were only necessary for product quality control and not for eliminating the chamber's EO. Both the maintenance leader and operations approved the bypass because they did not understand the purpose of gas washes when the chamber was empty. This flawed assumption directly led to the explosion. Throughout the incident, there were many instrumentation and control gaps. First, and most importantly, there was a lack of hazard understanding regarding the acid scrubber and the gas washes. In fact, the last time the operators had been trained that the acid scrubber only removes 60% of the EO was 7 years prior to the incident. This indicates that the system was highly susceptible to failure. Second, there was no gas concentration measuring device, alarm, or interlock in order to signify or impede upon flammable concentrations of gas from reaching the oxidizer. This means that the system was very susceptible to explosion. Finally, the glass in the control room was not blast-proof, as its shattering caused the only 4 injuries in the incident. There are many learning points to take from the incident. First and most importantly, operators should be trained on the design intent of every task expected of them. In this case, both the operators and their managers should have known that the gas washes are necessary to remove flammable content from the chamber and not just for product quality control. As such, it is imperative that only people that know the consequences of their actions should be given the authority to bypass. To conclude, this was a very preventable incident. Oxidizers are important yet risky pieces of equipment as they have air, fuel, and ignition all together in one source. As such, it is important that the criteria for bypass be held to a very high standard. In the future, any company hoping to use an oxidizer should consider multiple layers of safety, like controls, alarms, and interlocks, rather than relying on only one safeguard bypass.